Rotational motion is where a lot of physics students start to struggle, not because it's harder, but because it looks unfamiliar. In this video, we're going to connect rotational kinematics and energy directly to the kinematics and energy equations you already know, just rewritten for spinning objects. By the end of this video, you'll be able to use rotational kinematics equations confidently, understand how rotational and translational energy work together, and solve harder AP level rolling and rotation problems. So let's first talk about angular position, velocity, and acceleration. So let's look at the equivalencies between these two forms. Well, we have linear and rotational, obviously, linear or translational, and rotational. So you obviously have x and theta, v and w omega, and a and alpha. So this is angular displacement. This is angular velocity and angular acceleration. And what are the units for these? Well, that's pretty important. I'll also write the units for those. This is going to be measured in radians, and this is going to be measured in radians per second, and then this is going to be measured in radians per second squared. Now, let's talk about the rotation. Let's talk about the cake equations for these. Well, we know that it's going to be, we just have W is equal to W naught plus alpha times T. Theta is equal to theta O plus VOT plus 1/2 alpha T squared. And then W squared is equal to W initial plus 2 times alpha times the angle minus the angle initial. And this only, all of these apply. What is cake? The cake are constant acceleration. These only apply when you have constant acceleration in your problem, so be aware of that. And let's also do kinetic energy. So your kinetic energy is going to be K rotational is equal to 1/2 I squared. Kinetic energy is equal to 1/2 mv squared again. And then connecting these, we have the total energy for rotational motion that we've seen before is again just K total is equal to 1/2 mv squared. 1/2 times the angular acceleration squared. So now what is the, again, condition is that relates both of these is going to be V is equal to W times R. So what you need to know is that rotational kinematics describes how fast something spins. So this is how fast something spins, while rotational describes, sorry about that. This is rotational kinematics. And rotational energy represents how much energy that spinning represents. So also note that a larger, increase or a larger moment of inertia equals a smaller angular acceleration. And also that means that an increase or just more energy in rotation means that you have less translational speed, because the total energy is just the sum of both, and when you increase one, it decreases the other. So this is why shape matters more than mass in rolling motion. So again, let's do some practice problems to exhibit these. So we have a wheel that starts from rest and rotates with constant angular acceleration of 4 rad divided by second squared. How fast is it spinning after one complete revolution? So we know that if it starts from rest, that means W initial is equal to 0. And we know that alpha is equal to 4. And we know that one full revolution, we have theta is equal to 2 pi. So this means that we use the Cake equation of W squared, angular acceleration squared, is equal to angular acceleration initial squared plus 2 times the angular velocity squared is equal to the angular velocity squared initial plus 2 times the angular acceleration times theta. So that means that the angular velocity squared is equal to 2, plugging in our numbers. We have 2 times 4 times 2 pi, and this is going to be equal to 16 pi. And that means if we just want to get W, that means we just take the square root of both sides. So we have that W is just equal to 4 times the root of pi times radians divided by seconds. So in this equation, the reason why we use this equation because time is not given. And when time is not given, you have to use the Cake equation that is not defined in terms of time, because there's no way to solve for it. So now let's continue on to our second equation. A solid disk rolls without slipping from rest down a ramp of height h. Find the final speed at the bottom. So let's draw this out. Let's say we have this ramp and we have this solid disk, and the disk is like this. And we want to find the speed at the bottom. So we want to find VF. So we know that energy conservation is going to occur because here we know the initial energy is going to be just potential energy. And again, potential energy, we can just rewrite this as mgh. And then here we know that EF, that we're going to have EF, right? So that EF is going to be all kinetic energy again. And then this is going to be equal to 1/2 mv squared, right? So we can use energy conservation and write this as one expression so we can solve it as an equation. So using energy conservation, we know that E initial is equal to EF. Write this circle down here so we can visually represent that. And we have, E, this is supposed to be an F. Now we can write this on both sides. We have mgh is equal to 1/2 mv squared plus 1/2 I times the angular velocity squared. And remember, this is because up here, again, this was all translational because there had been no rolling. But after this, it rolls. There's rolling motion. And when there's rolling motion, it's basically like it's just spinning. It's like rotating. And some of that translational energy is converted into translational plus rotational energy because of the rotation that occurred for the ball to end up at the bottom. So because of that, now we know that also for a solid disk, the moment of inertia for a solid disk, which is something that you just have to know, is going to be I is equal to 1/2 mr squared. And you also know that the W is just going to equal to V over R. And so because we know this, we can substitute these values in. So we have we can just write this as capital M or just lowercase m, but we can just write mgh is equal to 1/2 mv squared. Let's actually make this into an I like this, and let's make this W into this so that this looks a little bit nicer when we're plugging everything in. So we have plus this plus, that's going to be plus 1/2. The moment of inertia was 1/2 mr squared, and then we have the W was just V over R, and then this is squared as well. Now just doing some simple algebra, this will simplify down to mgh is equal to 3/4 v squared. Now here we can clearly see that m just cancels out by dividing both sides by m. And then now what we want to do is we just want to solve for v. So then we're just going to multiply this by the reciprocal 4/3. And then now that this is canceled out, now we have to take the root of both sides. So then taking the root of both sides, then we're just left with the expression that v is going to be equal to the root of 4 times g times h divided by 3. And that is our solution. So now, remember that something that you have to be careful for in this problem is that if you forget that some of that translational energy was turned into rotational energy, you get the wrong speed because you had to account for that when you are calculating the speed. because some of that energy is converted into a different form that you have to represent like formulaically. So now we're going to do a question that links kinematics with energy. Now let's start. A wheel of radius r rolls without slipping with angular acceleration alpha. Find the linear acceleration of its center of mass. So let's just assume that it's rolling on a flat surface. And because it's rolling on a flat surface, we can represent it as this. So this is the center of mass, and this is just a wheel. So that's going to be the radius, and then it rolls without slipping. So what does that mean? That means that we can use the rolling condition. So what is the rolling condition again? So the rolling condition that we know is just V that relates the translational and rotational worlds. It's just V is equal to W or omega times R. We should actually say omega, not W. That's my bad. So then after this, you would differentiate both sides. Differentiate both sides. If you're in AB Physics 1, you don't have to necessarily know how to differentiate, because that's out of the scope of the class, but you just kind of have to memorize this variant. So this is going to be the solution. That's going to be the linear acceleration of its center of mass. So this equation, again, it allows you to switch between rotational kinematics and linear kinematics. So now, overall, for this topic, what you have to remember is that rotational kinematics, it mirrors linear kinematics. And you have to use the angular accelerations when acceleration is constant only. So these are only constant acceleration. It only applies when you have constant acceleration. And remember that V equals WR. This essentially is your bridge. This connects everything. This is your bridge. Again, and remember that shape, again, matters more than mass in rolling motion. All right, thanks for watching.